Welcome to the Deep Dive. Today we're getting into something really fundamental in electrical engineering, rectification. It's basically the essential bridge that lets almost all our modern electronics work. Think industrial controls, solid-state stuff. They all need DC, direct current.
Right, and they get it from the AC, the alternating current that comes out of the wall or the grid. Rectification is just that process, changing AC to DC.
So our mission today is to really get under the hood. Understand the circuits, the components, how this conversion actually happens safely and efficiently.
Exactly. We'll look at the building blocks, the math behind it, see why some circuits are, well, just better than others at giving clean DC power.
Okay, sounds good. So the plan is we'll tackle the main single-phase types first, then we'll ramp it up to three-phase systems for bigger power needs.
And then bring it back to a really practical application, battery chargers, specifically the kind you see in industrial settings.
Perfect. Let's dive in. All right, single-phase AC, that's what most of us have at home. When you need to convert that to DC, there are really two main ways engineers go about it, half-wave and full-wave.
Let's start with the simplest, the single-phase half-wave rectifier.
Simple sounds good. What does that involve?
Just one diode, that's it.
One. Okay. How does it work?
Well, the diode acts like a one-way valve for electricity. It lets current flow during one half of the AC cycle.
The positive half, usually.
Typically, yeah. And then it blocks the current during the other half, the negative half. So effectively, you're only using every second pulse of the AC power.
That sounds, well, like you're throwing away half the energy.
You are. And it shows in the output. The average DC voltage you get out is only about 31.8% of the peak AC voltage. So not very efficient.
31.8%. Wow.
Yeah. And the other thing is the ripple. Because you've got these gaps where the other half cycle was blocked, the output DC isn't smooth, it pulsates.
And the frequency of that pulsation, that ripple.
It's exactly the same as the input AC frequency. So if you've got 60 hertz coming in, you get a 60 hertz ripple going out. It's quite choppy.
Okay, so it's simple, cheap maybe, but pretty rough DC and inefficient. Why even use it then? Hasn't it been, phased out?
Not entirely. It pops up in really low-cost, low-power situations, maybe detecting a voltage signal or some basic LED indicators, stuff where the load just doesn't care about smooth DC, like a simple heater element.
Ah, okay. So niche applications.
Exactly. For anything that needs decent power quality, you move to full wave.
Right, because you want to use both halves of the AC cycle. So what's the first type of full-wave rectifier?
That would be the single-phase, full-wave, center-tapped rectifier.
Center-tapped. Okay, what does that mean?
It means you need a special kind of transformer, one where the secondary winding, the output side, has a connection right in the middle, the center tap.
Okay, and you need more diodes?
You need two diodes for this one. And the transformer center tap provides the return path. Basically, one diode handles the positive half cycle, the other handles the negative half cycle.
So they alternate, but the current always flows the same way through the load.
Precisely. You're using both halves of the AC wave now, and the payoff is immediate. The average DC voltage jumps up significantly.
How much?
It doubles, basically. It's 63.7% of the peak voltage now, much better than the half wave's 31.8%.
Okay, that's a big improvement. But needing that special transformer sounds like a downside. More cost, more bulk.
It definitely is.
Right.
That center tap transformer is more complex and expensive. And there's another detail. Those two diodes, they have to be tough.
How so?
When one diode is conducting, the other one is blocking, and it has to block the entire voltage across the secondary winding. That's a higher voltage stress compared to the other main full wave type.
Which brings us to that other type.
Yeah.
The one you see everywhere.
Yep, the single-phase full-wave bridge rectifier. This is probably the most common single-phase rectifier out there.
Why is it so popular? Does it avoid the transformer issue?
It does. It uses 4 diodes arranged in a kind of diamond or bridge shape. The clever part is how they're wired. It directs the current flow, so you don't need that center tap on the transformer.
4 diodes instead of 2, but you save on the transformer cost.
Exactly. And standard diodes are generally cheaper than specialized transformers, so from a manufacturing standpoint, it often makes more sense.
And the performance? Is the output voltage the same as the center tapped?
Identical.
Yeah.
Still 63.7% of the peak voltage. That 0.637 conversion factor is key for both full-wave types.
Okay, so same DC voltage output, but what about the ripple? Is it still better than half-wave?
Oh, absolutely. And here's the really important bit for both full-wave rectifiers, the center tapped and the bridge. The ripple frequency doubles.
Doubles, why?
Because you're getting a pulse of DC output for each half of the AC cycle. 2 pulses per input cycle. So if you put 60 hertz AC in,
You get 120 hertz ripple out.
Exactly. And that higher frequency ripple is much smaller in amplitude and way easier to filter out with capacitors. You get much smoother DC.
Ah, okay. That makes sense. Smoother DC, easier filtering. That's the big win for full wave. All right, let's step up the power. Single phase is common, but for industrial applications, big motors, heavy machinery, you often need three-phase power.
Oh.
And you need to rectify that too.
Yes, and when you move to three-phase rectification, the goal isn't just handling more power, it's also about getting even cleaner, smoother DC. The inherent nature of three-phase helps a lot.
How so?
Well, the three phases are offset from each other, right, by 120 degrees, so there's always a phase that's near its peak voltage. You don't have those valleys like in single-phase AC.
Okay, so even a simple three-phase rectifier should be better than a single-phase one. What's the basic type?
The three-phase half-wave rectifier. Similar concept to the single-phase half-wave, but now you have three phases.
So three diodes.
Three diodes, yes. And you need a connection to the neutral wire, so it requires a four-wire Y source connection.
And how does it work? One diode per phase.
Essentially, yes. At any given moment, only the diode connected to the phase with the highest positive voltage will conduct current. As the AC phases rotate, the diodes turn on and off in sequence.
Because the phases overlap, those gaps between pulses must be smaller.
Much smaller. And the result is a significant jump in performance. The average DC voltage is now 82.7% of the peak phase voltage. That conversion factor is 0.827.
Wow, 82.7%. That's way better than even the single-phase full wave's 63.7%.
It is. And the ripple frequency also increases, since you get 3 pulses for every 1 cycle of the input AC.
These 3 times the supply frequency, so 180 hertz ripple from a 60 hertz supply.
Correct. Already much smoother.
But just like single-phase, there's a full-wave version for three-phase too, right? For even better performance.
Absolutely. The king of the hill, really, for high-power DC is the three-phase full-wave rectifier.
Okay, how many diodes are we talking now?
This one uses 6 diodes, usually arranged in a bridge configuration, similar to the single-phase bridge, but, scaled up for 3 phases.
6 diodes. Does it still need the neutral wire?
No. Conveniently, it doesn't require neutral connection. It can work with a standard 3-wire, 3-phase source, either Y or delta. This is the workhorse you find in VFDs, industrial power supplies, things like that.
And the payoff for using 6 diodes, what's the magic number for efficiency here?
It achieves the highest conversion factor we've seen, 0.955.
95.5%. That's incredible. That's almost pure DC right out of the rectifier.
It's very close. The average DC output voltage is 95.5% of the peak line-to-line voltage value this time. We're getting really smooth DC.
So that 95.5%, almost pure DC, why is that purity so critical in, say, an industrial plant? What's the real-world impact?
Well, think about what that DC might be feeding. Often it's the DC bus of a variable frequency drive, or VFD, which then powers a motor, or maybe large DC motors directly.
Okay.
If you have a lot of ripple in that DC, it causes problems. It can create torque pulsations in the motor, making it vibrate, run hotter, wear out faster. It can cause noise in sensitive equipment.
So smooth DC means longer equipment life, better performance.
Definitely. And with the 3-phase full-wave rectifier, the ripple frequency is 6 times the supply frequency.
6 times, so 360 hertz ripple from 60 hertz AC.
Right. That super high frequency ripple is very small in amplitude and extremely easy to filter out completely. You get clean, stable DC power.
So the listener takeaway here is pretty clear. More pulses per AC cycle equals higher average DC voltage and a higher ripple frequency, which means smoother, cleaner DC power.
That's the core principle, from single-phase half waves 1 pulse all the way up to 3-phase full wave 6 pulses.
Okay, let's ground all this theory in something practical. A really common place you find rectifiers is in battery chargers. Not just the little ones for your phone, but bigger industrial units.
Yeah, think about backup power systems for data centers, emergency lighting banks, or even the chargers for fleets of electric forklifts. These need to reliably convert AC to DC to recharge batteries, often at 6, 12, or 24 volts DC.
So what are the main parts inside one of these industrial chargers?
Fundamentally, 2 main sections. First, you have a transformer. Its job is to step the incoming AC voltage down to something closer to the battery voltage you need.
And the second part is the rectifier stage we've been talking about.
Exactly. Taking that step-down AC and converting it to DC, usually it's a full-wave rectifier, often a bridge type, to get decent efficiency.
Now, many of these chargers have settings like low or high charge rate. How do they control the charging current? Is that in the rectifier part?
Usually it's done by adjusting the transformer. Many industrial chargers have a selector switch connected to different taps on the primary winding of the transformer.
The primary, the input side. How does that work?
By changing the tap, you change the number of turns on the primary coil that are being used. This changes the volts per turn ratio of the whole transformer.
So selecting high changes this ratio to increase the output voltage.
Precisely. It boosts the secondary AC voltage going into the rectifier stage. And even a small increase in the peak AC voltage, maybe just a volt or two, results in a significantly higher voltage difference between the charger and the battery.
Which pushes more current into the battery.
Right. More voltage difference equals more charging current.
Okay. Now, these industrial chargers, they can handle huge currents, right? Hundreds of amps sometimes. How do they manage that without components burning out? Are they using massive diodes?
Sometimes, but often they use a clever trick. Paralleling components. You might see multiple rectifier circuits working together.
Like running two bridge rectifiers side by side.
Exactly. Or maybe two single-phase, full-wave, center-tapped circuits in parallel, like one of the examples in our source material. If you use diodes rated for, say, 50 amps each, putting two sets in parallel allows them to share the current.
So 50 amp diodes could effectively handle 100 amps per leg if paralleled correctly, giving you a 200 amp total capacity.
That's the idea. It provides redundancy and allows for higher current without needing extremely large, expensive single components. It's about smart design for reliability.
That's a great insight. Now, let's talk about the actual charging process. There's this concept called tapered charging. What is that?
Tapered charging is kind of a natural behavior when you use a basic, unfiltered rectifier output to charge a battery.
Unfiltered, so just the raw pulsating DC.
Yeah. Remember, current only flows from the charger to the battery when the charger's instantaneous voltage is higher than the battery's voltage.
Okay.
So when the battery is very discharged, its voltage is low. That means for a larger portion of each DC pulse from the rectifier, the charger voltage is higher than the battery voltage.
So more current flows,
Yeah.
a higher average current.
Right. The current is initially high, but as the battery charges up, its own voltage increases.
So the voltage difference between the charger pulses and the battery gets smaller.
Exactly. Now, only the very peaks of those DC pulses are higher than the battery voltage. So, current flows for shorter durations. The average charging current automatically decreases or tapers off.
So it's a built-in safety mechanism slowing down the charge as the battery gets full to prevent overcharging and overheating.
Pretty much. It's a simple and effective way to charge lead-acid batteries, especially.
Okay, that makes sense. Now let's get to the really practical bit troubleshooting. Here's a scenario for you, based on the source material. You're checking a big industrial charger, supposed to be putting out, say, 10.8 volts DC average. You confirm the AC input is fine, but your meter reads only 5.4 volts DC, exactly half. What's your first thought?
Okay, AC input is good. DC output is exactly half of what's expected. That almost always points to a failure in the rectifier section.
What kind of failure?
Specifically, in a full-wave bridge rectifier, it means one pair of diodes has failed open. It stopped conducting.
One pair out of the four. So what did that do to the circuit?
It effectively turns the full-wave rectifier into a half-wave rectifier. You're only getting DC pulses from one half of the AC cycle again because the other path through the bridge is broken.
And that explains the voltage drop perfectly, right? Because the conversion factor changes.
Exactly. You go from the full-wave factor of 0.637 down to the half-wave factor of 0.318. That's pretty much exactly half.
So the average DC voltage measured by your meter gets cut in half.
Yep. The charger might still seem to work. It'll still put out some current, but it's going to take roughly twice as long to charge the battery. And the remaining diodes are likely under more stress due to the increased ripple.
That's a fantastic troubleshooting tip. Check the average DC voltage. If it's half of expected, suspect a failed diode pair. Hashtag tag outro.
All right, that was quite the deep dive. We went from the absolute basics, that single diode half-wave rectifier with its pretty low 31.8% efficiency.
All the way up to the 6-diode 3-phase full-wave system, hitting that impressive 95.5% conversion efficiency. And we saw how those core principles apply directly to everyday devices like battery chargers, including how to diagnose common failures. Those percentages, 0.318, 0.637, 0.827, 0.955, they really tell the story of rectifier performance.
They do. And remembering how the ripple frequency increases 1x, 2x, 3x, 6x the supply frequency, that directly relates to how smooth the DC output is, how easy it is to filter, and ultimately how well it protects the equipment it's powering.
Okay, so let's leave our listeners with a final thought, building on that troubleshooting nugget. We know a failed diode pair in a full-wave circuit halves the average DC voltage. But the peak voltage of those remaining pulses stays pretty much the same, right?
That's generally true, yes. The
Oh.
peak voltage hit in the load is still determined by the peak of the AC input minus the diode drops.
So here's a question for you to ponder. If you have a situation with normal peak voltage but half the average DC voltage, how might that discrepancy affect sensitive solid-state electronics that are maybe expecting smooth, consistent DC? A battery might tolerate it, albeit charging slower. But what about something more delicate?
hmm What other symptoms might show up besides just a low average voltage reading? Could that high peak voltage, combined with the low average and increased ripple, cause other kinds of failures or malfunctions?
Something to think about next time you're looking at a DC power supply that's acting strangely. Thanks for joining us on the Deep Dive.